Hello folks, welcome back to Physics Online, where today we're going to talk about using vector components to add vectors. But first, a little review. What is a vector? A vector is a quantity that has both what and what. What's the steps for adding two or more vectors? Step 1, we add vectors by connecting the tail of one vector to the blank of another vector. Step 2, the vector sum or resultant vector is found by connecting the blank of the first vector to the blank of the last vector. So you're going to be filling in those blanks. In addition, solve these two examples. Example number 1, suppose we have two displacement vectors. Vector A is 3 meters in the positive direction. Vector B is also in the positive direction, but it's 5 meters. And you want to find the vector sum by using this vector addition process. That is, find the resultant, which is the sum of vector A and vector B. In addition, example number 2, suppose we have two displacement vectors, vector A, positive 3 meters, but vector B is negative 5 meters. What's the vector sum? Again, using the two-step process for adding vectors. So push that pause button, and then we'll come back and compare answers. Let's see what we have for answers. Of course, a vector quantity has both magnitude and direction. And the two steps for adding vectors. First step is add vectors by connecting the tail of one vector to the head of another. The second step, of course, is to find the resultant is found by connecting the tail of the first vector to the head of the last vector. And here's an example. Suppose we add these two vectors, vector A. So here's vector A right here. We're connecting the tail of vector B to the head of vector A, like so. To get the resultant, we go back to the tail of my first vector, vector A, and connect it to the head of my last vector, vector B, and as we can see, the resultant is 8 meters. Example number 2, again we have a vector A in red, and it's 3 meters in the positive direction. Adding vector B, but it's going in the negative direction, we connected the tail to the head. And to get my resultant, you go back to the tail of the first, connect it to the head of the last, and the resultant in this case is negative 2 meters. From this, we can draw some conclusions. We conclude that vectors lying in the same or opposite directions can be added algebraically to get, well, to get what? Well, to get the resultant or vector sum. So fill in that blank right in here after you push the pause button. So we conclude that vectors that lie in the same or opposite directions can be added algebraically to get the resultant or vector sum. That's what we did in the previous two examples. We simply added up them algebraically to get my final resultant vector. Now, what if we have a vector A, which is 10 meters in magnitude at a 45-degree angle north of east? In other words, down here, here's vector A at an angle of 45 degrees north of east. And we have a vector B that's also magnitude 10 meters, but it lies in a direction 30 degrees south of west. I'm going to add these two vectors, A plus B. Now, if we add them, is our resultant going to be 20 meters? Yes or no? Well, you should see that these vectors have different directions. They don't lie along the same direction or opposite direction, so we can't simply add them up algebraically. 10 meters, 10 meters gives me 20 meters, but that's not the correct answer. And we can see that by simply using our rules for adding vectors and finding the actual resultant. So here's vector A at an angle of 45 degrees. Here's vector B, which is 30 degrees south of west. So in other words, here's my angle 30 degrees. If I went due west, I'd go this way, but I got to go 30 degrees toward the south to get on my vector B. So this is my vector B, and I'm connecting the tail of vector B to the head of vector A, the tail to head method. And we know that to get the resultant, we go back to the tail of my first vector, that's vector A, and connect it to the head of my last vector, vector B. In other words, this is the shortest distance between my starting point and my ending point, and that is how we define the resultant. The question is, what is the value of that resultant? What's the magnitude, and what is the direction? That is, we need to know what this angle is right here. So that's going to be our next step. So we want to find the vector sum of vector A plus vector B. And we can use vector components to find this resultant of this vector addition. Any vector can be resolved or broken up into two perpendicular components. For example, let us break vector A into its x and y components. Remember, vector A is 10 meters at an angle of 45 degrees north. Here's vector A right here. And we're going to break it up into an x component, which I'm going to call a sub x, and a y component, which I'm going to call a sub y. And see if you can use some trigonometry to write down what trig function you're going to use, and then write down the numerical value for the x component and the numerical value for the y component. And then the question is, do these vector components add up to get, that is, the resultant being vector A? Are these really the two components? Will they add up to get vector A? And we can check this, since this is a right triangle, we can check it by using Pythagorean theorem. So first find these two components and then use the Pythagorean theorem down here to see if they really do give us the magnitude of my resultant vector A. So push that pause button and we'll return in a few seconds. Okay, let's see what we have. For the x component, that is, that component that lies along the x-axis, we can find that by using the cosine function. The cosine of 45 is the adjacent a sub x over the hypotenuse A, and therefore that component a sub x is a times cosine 45, or 10 meters, which is the magnitude of vector A, times the cosine of 45, comes about 7.1 meters. For the y component, that is the component that lies in the direction of the y-axis, its value is, you can find this value by using the sine. The sine of 45 is the opposite over the hypotenuse. And solving for a sub y, we get a sine 45. Again, the magnitude of vector A is 10 meters. Sine of 45, 0.707, multiply the two together, it's around 7.1 meters. So both of these components, ax and ay in this case, have the same magnitude, although one lies in the x direction and the other lies in the vertical direction. And we can check that these components, a sub x and a sub y, really do add up to vector A. Since it's a right triangle, we can use the Pythagorean theorem. 10 squared, that's the magnitude of vector A, should equal 7.1 squared plus 7.1 squared. And indeed, 7.1 is around 49, 7.1 around 49. They add up to be pretty close to 100. So the Pythagorean theorem checks. Now let's take a look at our other vector, vector B. Remember, it was 10 meters north at an angle of 30 degrees south of west. And we want to resolve that vector into its x and y components. Another way of saying it is that we want to break that vector down into its x and y components. So first, we're going to do the same thing that we did with vector A. We're going to place it at our origin, and keeping in mind that its direction is this way, that is, it's at an angle of 30 degrees south of west. If I want due west, I go this way, but I have to go toward the south by an angle of 30 degrees to get on my vector. And what we're going to do is draw the x component, which is this way, b sub x. You're going to draw the y component, which is this way, b sub y. And you're going to use a trig function and come up with the values for those two components, b sub x and b sub y. And be careful about the signs. And then to check to see if they really do add up, vectorially to vector b, you can use the Pythagorean theorem, because what we will have here is a little right triangle. So push that pause button, and we'll come back and compare results. Okay, let's see what we've got here. Here's our component in the x direction, b sub x, and notice it's going in the negative direction. Here's our component b sub y. It's going in the y direction, but also in the negative y direction. These components add up to give me my resultant. Remember, connecting the tail of one to the head of the other. Go back to the tail of the first, connect to the head of the last. So this is my vector sum. B vector really is equal to the vector sum of b sub x and b sub y, according to our rules for adding vectors. Now, to evaluate this component b sub x, we're going to have to use the cosine. The cosine of 30 is the adjacent over the hypotenuse. And so solving for b sub x, we get negative b, because it was located in the negative direction, negative b cosine of 30 degrees. B, remember, is negative 10 meters. So it's negative 10 meters cosine of 30. It should give us negative 8.7 meters as my magnitude and direction for b sub x. It's in this direction, 8.7 meters. Now for b sub y, as you can see, b sub y is basically involves the sine. The sine of 30 degrees is opposite of the hypotenuse. Solving for the opposite, we get b sub y equals minus b sine 30 degrees. Again, minus because we're talking about going down in a negative direction. And then that's equal to minus 10 meters sine of 30, which gives me negative 5 meters. So in other words, if we went negative 8.7 meters this way along the negative direction, and then we went negative 5 meters this way, we would be able to be on our vector, vector b. And do the components add up? Well, we can check it by using Pythagorean theorem. Vector b is indeed 10, square it. This x component is negative 8.7, square it, and add it to the component b sub y after you squared it, and they should be fairly close to being equivalent. Of course, we did some rounding here, so they won't come out to be exact, but they should be fairly close. Now we can use the component vectors of vector A and vector B to find the vector sum. Remember, we wanted to find the vector sum, r equals the sum of vector A and vector B. In other words, remember what we wanted to accomplish. We wanted to find my vector sum, which is basically this resultant right in here. We've broken vector A up into x and y components. We've broken vector B up into x and y components. And now we want to find this resultant of the vector sum of A and B. Okay, now we need to organize our work a little bit. So to do that, we're going to set up a table. And I advise you to do this when you do the homework to help organize our work. And in this table, you're going to have a column in terms of the vectors we're dealing with. We're dealing with vector A, and you're going to write in its x component and its y component. And then we also had a vector B, and you'll be writing in its x component and its y component. And remember, when the x components, they lie along either the same or opposite direction, you can simply add them up algebraically, and this will allow us to find my resultant. It's simply the sum of vector A and vector B. Now actually, this component right in here, let me change it a little bit, this component is actually going to be the x component of my resultant, because we simply added up the x components of A and B. This component right in here is actually going to be the y component of my resultant, because we are adding up the y components of vectors A and B. So when we talk about the resultant, what we really get in this table, we will get the x component of the resultant and the y component of the resultant. So fill in those values, and let's see if you can come up with the correct values for r sub x and r sub y. Push that pause button, and we'll return in a few seconds. So here's what we get. The x component For vector A was a cosine 45, which is 7.1 meter, and the y component was a sine 45, which was also 7.1 meter. For the vector B, its x component was minus b cosine 45, which was equal to negative 8.7 meters. And for the y component, vector B, it was minus b sine 45, or negative 5 meters. Now to get my resultant, because these vectors right here lie right along the x-axis, okay, we can simply add them up algebraically, and when we do so, we get the x component of my resultant, negative 1.6 meters. In other words, down here, here's my x component of my resultant. It's in the negative direction, and that value would be 1.6 meters negative. The y component is found again, because these lie along the y-axis. We can add them up algebraically. You get a positive 2.1 meter. So over here, here's my y component. We're connecting tail to head. It's in the positive direction, 2.1 meter. And now, the final steps are this. You're going to use the Pythagorean theorem to find my resultant vector r. And you're going to find this angle right in here using inverse tangent. So in this space right here, use the Pythagorean theorem to find the magnitude of my resultant, and use the trig function to find my angle and therefore the direction for my resultant. So push that pause button and we'll come back and compare answers. So this is what I found. My resultant was found by using the Pythagorean theorem, the square root of negative 1.6 squared plus 2.1 squared, and it gave me the resultant with a magnitude of 2.6 meters. To get this angle right in here, this angle theta, I'll use the inverse tangent. It's the opposite, which is r sub y, over the adjacent, which is r sub x. And notice I'm only going to keep the magnitude of those values, 2.1, and I'm going to keep 1.6, not negative 1.6, but 1.6, because I know my angle will always be less than 90 degrees if I keep the values here positive. When I do that, I find the angle to be 53 degrees north of west. In other words, I'd have to go, if I want to do west, I'd go this way, but to get on my vector r, I'd have to go 53 degrees toward the north. So in other words, the resultant, which is the vector sum, a plus b, is equal to the magnitude of 2.6 meters at an angle of 50 degrees north of west. And to go back and revisit the original problem and see what we did, back here, what we did is we broke up vector A into x and y components, an x component here and a y component here. We broke up vector B into an x component and a y component. We added up the x components and y components to find the x component of my resultant and the y component of my resultant, and then we used the Pythagorean theorem to actually find the value of my component and also the direction as well. So this is what we do in terms of adding vectors by using component vectors. And as you can see, it can be a little bit complex, but your work can be more organized if you set up a table in this manner and put down the various components and show all the work. And even if you get the wrong answer at the end, if I can at least see the work done, then I can give you some partial credit. So that's it for vector components. I thank you for tuning in, and I hope you learned some physics.